In the vast expanse of theoretical computer science, there exists a fascinating realm known as formal language and automata theory. This field delves into the intricate study of abstract machines and the languages they can recognize. At its core, this field explores the fundamental properties of computation, seeking to understand what can be computed and how. Formal language and automata theory provides a rigorous mathematical framework for defining and analyzing these computational models. Imagine a world where machines could understand and process languages with the same precision as humans. This is the world that formal language and automata theory seeks to unravel. Automata theory deals with the abstract models of computing devices known as automata. These automata process information based on a set of rules and transitions, much like how computers execute programs. By studying automata, we gain insights into the capabilities and limitations of different computational models. Together, formal language and automata theory provide the foundation for many areas of computer science, including compiler design, programming, language theory, and computational complexity. It is a testament to the power of abstraction and the elegance of mathematical reasoning. The impact of formal language and automata theory extends far beyond the realm of theoretical computer science. Its principles have found widespread applications in various disciplines, shaping the way we interact with technology and understand the world around us. In computer science, formal languages form the backbone of programming languages. Compilers, the unsung heroes of software development, rely heavily on formal language theory to parse and translate code into machine-readable instructions. The design and analysis of algorithms, the heart of computer programming, also benefit from the principles of automata theory. Linguistics, the scientific study of language, has also been profoundly influenced by formal language theory. By modeling natural languages using formal grammars, linguists can gain a deeper understanding of syntax, semantics, and the underlying structure of language. This has led to advancements in natural language processing, machine translation, and speech recognition. The field of engineering has also embraced the principles of formal language and automata theory. From designing digital circuits to modeling complex systems, engineers use automata theory to ensure the correctness and efficiency of their designs. Formal verification techniques rooted in automata theory are crucial for verifying the safety and reliability of critical systems. To embark on our journey into the world of formal languages and automata theory, we must first familiarize ourselves with some fundamental concepts. These concepts form the building blocks upon which this fascinating field is built. At the heart of formal language theory lies the concept of an alphabet, denoted by sigma. An alphabet is simply a finite set of symbols. These symbols can be anything: letters, numbers, or even special characters. For example, the English alphabet, the set of digits 0, 1, 2, and so on up to 9, and the set of binary digits 0 and 1 are all examples of alphabets. A string is a finite sequence of symbols chosen from an alphabet. For instance, hello 1, 2, 3, 4, 5, and 0, 1, 0, 1, 0, 1 are all strings over their respective alphabets. Strings are the fundamental units of data in formal language theory. We use them to represent information and manipulate it using formal rules. Finally, we come to the concept of a language. A formal language is a set of strings, all of which are formed from a specific alphabet. For example, the set of all valid English words, the set of all binary numbers, and the set of all syntactically correct Java programs are all examples of formal languages. Section 4. Constructing languages, from alphabets to complexity. Formal languages are not merely random collections of strings, they possess structure, a well-defined organization that sets them apart from arbitrary sequences of symbols. This structure arises from the way languages are defined and the rules that govern the formation of valid strings, ensuring consistency and coherence. Understanding how languages are constructed is key to unlocking the power of formal language theory, which has applications in computer science, linguistics, and beyond. We begin with an alphabet, the fundamental building blocks of our language, consisting of a finite set of symbols. From this alphabet we can generate strings by concatenating symbols together, forming sequences that can be analyzed and manipulated. For example, if our alphabet is A-B, we can form strings like AB, AAB, BABA, and so on, each representing a unique combination of the symbols. However, simply concatenating symbols does not give us a language. It merely provides us with potential strings. To define a language, we need rules. a set of guidelines that determine which strings are valid and which are not. These rules, often expressed as formal grammars, dictate which strings are allowed in the language and which are not, providing a clear framework for language construction. Formal grammars provide a mechanism for generating valid strings in a language, ensuring that each string adheres to the predefined rules. They consist of a set of production rules that specify how to replace certain symbols with other symbols or sequences of symbols, guiding the transformation process. By repeatedly applying these production rules, we can generate all possible strings in the language, exploring the full range of expressions it can produce. The complexity of a language is determined by the complexity of its grammar, with more intricate rules leading to more sophisticated languages. Simple languages, such as the set of all binary strings with an even number of zeros, can be described by relatively simple grammars, making them easier to understand and implement. In contrast, complex languages, such as natural languages or programming languages, require more sophisticated grammars to capture their intricacies, reflecting the richness and diversity of human communication and computational logic. Section 5. Regular languages, patterns and expressions. In this section, we delve into the fascinating world of regular languages and their applications. Within the vast landscape of formal languages, regular languages stand out as a fundamental and widely studied class. They form the backbone of many computational theories and practical applications. These languages, characterized by their simplicity and elegance, find applications in various domains, from text processing to compiler design. Their utility spans across different fields, making them indispensable in computer science. Regular languages are those that can be described by regular expressions, a powerful formalism for specifying patterns in strings. This formalism allows for precise and efficient pattern matching. Regular expressions provide a concise and flexible way to define sets of strings based on shared characteristics. They are tools that can be wielded with great precision to solve complex text processing problems. For example, the regular expression A describes the language of all strings, consisting of 0 or more A's followed by 0 or more B's. This simple example illustrates the power and versatility of regular expressions. The beauty of regular languages lies in their close relationship with finite automata, another fundamental concept in automata theory. This relationship is both deep and profound. Finite automata are abstract machines that can recognize regular languages. They serve as a bridge between theoretical concepts and practical implementations. These machines, with their limited memory, provide a simple yet powerful model of computation. Despite their simplicity, they are capable of performing complex tasks. Regular expressions and finite automata are two sides of the same coin. Understanding one often leads to a deeper understanding of the other. Every regular expression can be converted into an equivalent finite automaton, and vice versa. This equivalence is a cornerstone of automata theory. This duality allows us to seamlessly transition between these two representations, choosing the one that best suits our needs. It provides flexibility in both theoretical analysis and practical application. Examples of regular languages abound in computer science. They are integral to many systems and processes. Lexical analyzers, the first stage of a compiler, use regular expressions to identify tokens in source code. This process is crucial for the correct interpretation and execution of programs. Text editors and search engines rely on regular expressions for pattern matching and searching. These tools enhance our ability to manage and manipulate text efficiently. Section 6. Context-free languages, grammars, and structures. Venturing beyond the realm of regular languages, we encounter the fascinating world of context-free languages, a domain rich with complexity and potential. These languages, possessing greater expressive power, play a pivotal role in defining the syntax of programming languages and modeling hierarchical structures. They allow us to create more sophisticated and nuanced models of language. Context-free languages, as their name suggests, are those that can be generated by context-free grammars. These grammars consist of a set of production rules that define how strings in the language can be generated. Unlike regular grammars, context-free grammars allow for more flexible production rules, enabling them to describe languages with recursive structures. This flexibility is what gives context-free grammars their power and versatility. For example, a context-free grammar can easily describe the language of well-balanced parentheses, a task that proves impossible for regular grammars. This is because context-free grammars can handle nested structures, which are essential for balanced parentheses. The power of context-free languages lies in their ability to capture nested structures and dependencies. This makes them particularly useful in fields where such structures are common. This makes them ideal for defining the syntax of programming languages, where nested constructs like loops, conditional statements, and function calls are commonplace. Without context-free grammars, it would be challenging to accurately describe these constructs. Context-free grammars provide the formal foundation for parsing, the process of analyzing the syntactic structure of a program. Parsing is a critical step in compiling and interpreting code. Beyond programming languages, context-free languages find applications in various domains. Their ability to model complex structures makes them valuable in many areas of study. In linguistics, they are used to model the syntax of natural languages, albeit with some limitations. While not perfect, they provide a useful framework for understanding language structure. In compiler design, they form the basis for syntax analysis and code generation. This is crucial for transforming high-level code into machine-readable instructions. Examples of context-free languages include the language of palindromes, the language of arithmetic expressions, and the language of XML documents. Each of these examples showcases the unique capabilities of context-free grammars. These languages highlight the versatility and expressive power of context-free grammars. They demonstrate how these grammars can be applied to a wide range of problems, making them an essential tool in both theoretical and practical applications.